Hello, welcome to the fifth and final installment of this series where we are proving the circle theorems. Now I know in some books there are more than 5, but I consider these to be the main 5. So this one possibly the most tricky to understand what's going on. It's called the alternate segment theorem. So what does it say? When we have a tangent and a chord, remember a chord's a line across a circle, the angle formed between the tangent and the chord is equal to the angle on the other side of the chord. So essentially, DCE is our tangent here in this diagram, and this is the angle formed between the chord, BC, and the tangent. And what it's saying is, well, this is one part of the segment here, so I'll just highlight that. And the angle in the other segment is this one. Okay, so we're trying to prove that these two angles are equal. And there's a few ways to go about doing this. But the way I like the best is, again, making use of radii and isosceles triangle. So we've got O to C. Let's draw O to B as well. So O to B is there. And finally O to A. There we go. And these are all radii, so I'll write that down. So O to C, O to B, and O to A are radii, which in particular means they are the same length. So this is the same as this, which is the same as this. And we now have 3 isosceles triangles. Just before that, we also noticed that if we have a radius and a tangent, then they are perpendicular. Radius is perpendicular to tangent, so i.e. DCE is perpendicular to OC, and this tells us that this whole angle here is 90. Okay, so that's important. Right, now let's do what we have been doing with isosceles. We know that the base angles are equal, so let's start with this one. Let's call these two angles x. That's just basics of an isosceles. These two angles y. And finally these two angles, let's call them z. So we've got x, y, z. Right, and let's take a look at the angle we are trying to prove. So we're trying to prove that this angle here is equal to this one. So this angle at the top is y plus z. And what is this angle here? Well, as we've previously said, because DCE is perpendicular to OC, this whole angle here, this whole angle must be a right angle. So this tells us that the purple angle must be 90 take away x, because then we'll have x plus 90 minus x, which equals 90. Good, so we've got our angle there. Now what else can we do with this? The only other thing we can really do at this point is use the fact that angles in a triangle add to 180. So let's do that. Okay, so angles in a triangle add to 180. We know this. And our triangle is ABC. Add to 180. In particular, let's add them all up. Well, we've got x plus z plus x plus y plus y plus z. Right, and we can simplify this, so let's do that. Well, we've got 2 lots of x, we've got 2 lots of y, and we've got 2 lots of z, equal to 180. What can we do from there? Well, we can divide by 2, so let's do that. So this tells us that x plus y plus z equals 90. And from here, hopefully you can see that if we take away x on both sides, we get y plus z equals 90 take away x. And this is exactly what we were trying to prove. Remember, this angle we're looking for is 90 minus x, and this angle up the top is y plus z. So, we're done. We've proved that the angle formed by the chord and the tangent is equal to the angle in the opposite segment. So this does conclude our series on circle theorems. Let me know if I've missed anything. Have a nice day, guys. See you later.